Here's an example of a somewhat real-world example. This is how they would test buses. And I wanted to put, I know the chart is a little bit hard to read, but in this case, what you have is a driving profile for a bus that uses supercapacitors. And what's happening here is, as you accelerate, that's the first step. That goes from 0 to 10 seconds, right? So that's a fairly long acceleration time for a bus to be accelerating, at least in Jodhpur. If you can accelerate for 10 full seconds, you're probably on the heels of someone else, right? Anywhere in India. But imagine that it's out on the highway. So the bus is accelerating, and what's happening? The voltage in the capacitor, these are two different capacitors, one at the beginning of life and one at the end of life. The voltage in the capacitor is dropping. Why? Because we're drawing current out of the capacitor, using it for the acceleration. So it's driving a motor, okay? Then the bus has reached its full acceleration and it goes to steady speed. And during the steady speed stage, there's a small amount of power that goes back into the capacitors to recharge them. You can see that right here, where there's a slight upward drift in the voltage. So that would suggest there's a constant current going in, that linear voltage. If voltage is increasing in time, that means the rate, the voltage rate, dV dt, is constant, which means that if you have a constant capacitance, you have a constant current going into your device. Then what happens here is your bus hits the brakes. There is regenerative recovery of energy. So in your brakes, you have some magnet system that recoups. It's an inverse motor. The magnet system actually causes a deceleration, right? And that energy is picked up in your supercapacitors. It's something that's it's highly energetic, right? If you look at this scale, right, your peak power during acceleration was only about, I'd call that about 85 kilowatts. But during regeneration, you're actually putting in 150 kilowatts into your device. That's why capacitors are used for this, because batteries would become probably overheated. They couldn't take in that much power so quickly, and so that's why capacitors are such a good example. And during this regeneration time, you see a very, very large initial increase in the voltage, right? And then it tapers out. It tapers out as you transition. There may be some overvoltage happening here. There may be some excess charge happening here. Maybe this capacitor can't quite take all of that current, and that's why you see a peak in the capacitor voltage. There's something going on here that's probably not ideal, because you're still regenerating at that point in time. And then you go into, once you've braked, then you go into the steady mode of constant speed again, or stoppage. I think in this case, actually, this was a full stop, but the engine is running. And so full stop while the engine is running, you can also draw some energy off of your engine during that time. So this is a real-world example that I wanted to leave you with. But if you look at this, here you're talking about potentially, of course, maybe not full, but a significant charge and discharge cycle in less than a minute, right? Less than a minute. And that's another reason why supercapacitors are the material of choice, or the technology of choice, for automotive applications, for electric vehicles and hybrid vehicles. It's because this very energetically significant event happened in less than a minute. And how many times in a day would that happen, right? How many cycles of that would we have in a day with a bus? I would say hundreds, maybe 1,000 of those cycles in a day. And a battery, as we said, typically is going to start to show significant decay and degradation after 1,000 or 2,000 cycles, which means that those batteries would work on that bus for about a day or a week, and that's no good, right? You don't want to be changing those out. We want something that would have millions of miles, or millions of cycles, right? And so that's why supercapacitors, in this case, these would probably be double-layer supercapacitors. Something with a really good cycle life would be the technology of choice for that. All right. So with that, I will conclude my lecture, and I will be happy to take questions. Any questions? Yes.
Sir, when we connect the number of cells in series, and you have said that the life aging becomes faster.
Yes.
What is the basic reason behind this?
Because there are potentially voltage imbalances that can cause faster aging in series cells that are independent of, they can actually cause an individual cell to fail faster. But generally speaking, if you put these devices in series, then if one fails, then the entire bundle will fail. If you put them in parallel, you're giving some bypass avenues. And so, in essence, by putting these capacitors in series and then having one fail, you're saying, in essence, that when one fails, they all fail. I guess is the way to imagine that.
As far as solar cells are concerned,
yeah.
You know that the single solar cell having a small amount of voltage, which not serve the purpose.
Yeah.
We have to connect the number of cells in series.
Yeah.
The same criteria can happen in case of solar cells.
Right. Absolutely. In fact, I have a friend, Ashraf Alam, who works on how to optimally distribute the circuitry of solar cells. You have to stack some, right, because you want to be generating a higher voltage. A typical solar cell is going to only generate about a volt, a little bit less. And so you want to be able to, you have to be able to put those, a few in series to get your voltage up. Maybe, I don't know how many the typical is. If you're trying to create a 24 volt output, then you'd have to put about 24 together. And then what you would do is, if you have one zone of your solar cell that goes bad, you don't want it to affect anything else. But whatever you're doing in your series stack with a solar cell, if one of those in the series stack fails, then that section will fail. Yeah. But that is a technology. So one of the challenges with flexible solar cells and organic solar cells is wiring them together in the proper way and keeping that flexible as well. More questions? No? All right. If not, well, we have a really, I think, fun event planned now. Another tutorial on battery assembly. So I will let Dr. Gupta take it from here.